So now let's consider limits at infinity, or negative infinity. What happens is if the input increases without bound, whether that's in the positive direction or negative direction. So again, let's consider a graphical example, and let's go back to that graph of the function 1 over x squared. And so I'm going to think about two limits. What is the limit as x approaches infinity of the function? And what is the limit as x approaches negative infinity of the function? Alright, so if x is approaching infinity, that means that x is becoming a very large positive number. And so that's what's happening in this part of the graph. As x is moving further and further to the right, what is happening to the function? Well, if x is approaching a large number, then I have 1 divided by a large number. And if I have a regular, real number divided by a large number, that limit goes to 0. And a similar thing happens on the left. The limit as x approaches negative infinity of the function, that's this part of the curve. As we're moving further and further to the left, then again, the function, I have 1 divided by a large negative number squared, which then becomes just 1 divided by a large number. And this limit is also 0. Now that doesn't mean that every time we take a limit at infinity we get 0. That's just what's happening for this curve. But we can state in general, if n is a positive number, if n is positive, then the limit as x approaches either a positive or negative infinity of 1 over x to the n, that limit will equal 0 as long as n is a positive number. And we won't prove this, but it should seem reasonable to you if you think about what's happening here. Alright, so let's look at some more complicated examples. But we're going to need this fact. So this fact here is important. Let's remember this fact, that the limit as x approaches infinity or negative infinity of 1 over x to the n, as long as n is positive, that's going to give us 0. We're going to need that. Alright, so let's take a look at a few limits here. So we have the limit with x approaching infinity of 3x squared plus 5x minus 7 over 6x cubed plus 3x squared minus 6. You might think, well, I don't know, what's happening here? If I let x approach infinity, I don't have any divisions. I don't know what to do with this. And you might even say, well, I know that if I let x approach infinity, if I square an infinite number, that's still an infinite number. So it looks like this numerator goes to infinity, and the denominator appears to go to infinity as well. And if you remember back, that's an indeterminate form. Infinity over infinity is indeterminate, so we have to come up with an approach for this. So here's what we do. If we're finding a limit at infinity, and we have a rational expression, what we try to do is divide through, or really multiply through, the numerator and denominator by a certain quantity that's going to make things work for us. And so what I'm going to do is I'm going to go through this and figure out what is the highest degree. I see an x cubed, right? I see this x cubed here. So what I'm going to do is I'm going to multiply both numerator and denominator by 1 over x cubed. And so then this becomes the limit with x approaching infinity. All right, and applying the distributive property then, this gives me 3 over x plus 5 over x squared minus 7 over x cubed. In the denominator, I have 6 plus 3 over x minus 6 over x cubed. Now, remembering what we saw on the previous slide, the limit at infinity of something of the form 1 over x to the n goes to 0. And so it turns out that if it's any real number over x to the n, the limit at infinity will go to 0. So what happens here? If I let x approach infinity, 3 over x becomes 0. 5 over x squared becomes 0. 7 over x cubed becomes 0, minus, whatever. Adding 0, subtracting 0, inconsequential. In the denominator, I have 6 plus 0 plus 0. So I have 0 divided by 6, which is 0. So this limit, as x approaches infinity, would be 0. Now in the second example, I changed it up a little bit. Notice now that in this case, the highest, it's a similar expression, except now I've changed the denominator to be a 6x squared. So if I use a similar method, a similar idea, I would multiply the numerator and denominator by 1 over x squared. And then this gives me the limit with x approaching infinity of 3 plus 5 over x minus 7 over x cubed, x squared, excuse me, over 6 plus 3 over x minus 6 over x squared. Applying the limit at infinity, that gives me 3 plus 0 over 6 plus 0 plus 0, 3 over 6, 1/2. If we let x approach infinity on this last expression, now again notice I've changed it up a little bit. Now the denominator is linear and has degree 1, right? And so now the highest degree that I see is still x squared. So again, I'll multiply by 1 over x squared in both the numerator and denominator. And this gives me then the limit with x approaching infinity. And then that would give me 3 plus 5 over x minus 7 over x squared over 3 over x minus 6 over x. And so then, now this gives me 3 over 0. 6 over x squared. So here, got to be a little bit more careful with this one. Because we have a division by 0, so this is undefined. So we have to be a little bit more careful with this one. We can't leave 3 over 0. What we need to do is decide what's happening here. All right, well, certainly the numerator is positive. And what's happening in the denominator? I have 3 over x. So that's going to be a small, that's going to approach 0 on the positive side, minus 6 over x squared. 6 over x squared, that's going to approach 0 on the positive side as well. And that 6 over x squared is going to be a smaller number than 3 over x. So that's going to give me a small positive number in the numerator. And so then this is an infinite limit. And so what we've seen here is we have 3 examples, and they're all quite similar. But we get 3 different results. I've got a limit at 0 for the first one, a limit of 1/2 for the second one, and an infinite limit for the third example. But again, they're all quite similar. And you might remember this having something to do with horizontal asymptotes for rational functions back in an algebra course, and this is related. You probably just learned something to memorize, that if the degree in the denominator was greater, then you had a horizontal asymptote at 0. If the degrees in the numerator and denominator were equal, then you took the lead coefficients, the ratio of the lead coefficients, 1/2 as the horizontal asymptote. And if the degree in the numerator was greater, then there wasn't a horizontal asymptote. Now, and there's a little bit more to it than that. What we can also say is, if we take the lead terms on this one, so if I take the 3x squared and the 3x, if I take the lead terms and I find their ratio, this behaves, right? So this, if I take that 3x squared over 3x, this is approximately x. And so what this is telling me is, for large values of x, (3x squared plus 5x minus 7 over 3x minus 6) behaves like, is approximated by, just simply x. And so if we think of the curve x, right, well, that's just a line, right? As I move far to the right, positive infinity. If I move far to the left, negative infinity. All right, so what that's also telling me is that if I was to change this up a little bit, if I said, what's the limit with x approaching negative infinity of 3x squared plus 5x minus 7 over 3x minus 6? That limit is negative infinity. So now let's look at a few other situations. Limits at infinity involving square roots can be a little tricky to deal with. And so one thing that we want to be aware of is, if we think about it, if I think about the expression x squared plus 9, and I let x approach infinity, there's not much difference between x squared plus 9 and x squared. So what I would say for this is, if we had the limit as x approaching infinity of the square root of x squared plus 9 over 2x, this is similar. This is approximately the limit as x approaches infinity of the square root of x squared over 2x. Now, it's very tempting to say, well, the square root of x squared is x. And that's not correct. We have to be very careful about roots and powers because of one-to-one functions, really, from back in algebra. Here is something that's true. So, the nth root of x to the n is equal to two different things depending on the root. The nth root of x to the n is equal to x if n is odd. The nth root of x to the n is equal to absolute x if n is even. All right, just as a quick example to show why this seems reasonable, what's the square root of negative 2, what's the cube root of negative 2 cubed? All right, well, negative 2 cubed is negative 8, and the cube root of negative 8 is negative 2. It gets back to where we started. And if you remember, the cube root and cubing are both one-to-one functions and inverses of each other. However, the square root of negative 2 squared would be the square root of 4, which is 2. Because remember, the squaring function is not 1-to-1. And so there are issues with that situation. So the square root of negative 2 squared is the square root of 4 is 2, which is the absolute value of negative 2. So this statement is legitimate. Now, going back to our exercise, that means then that the limit as x approaches infinity of the square root of x squared over 2x is the limit with x approaching infinity of absolute x over 2x. All right, now I can drag the factor of 1/2 outside the limit. Now, absolute x over x, if x is a positive number, let's think about this. Now, x is a positive number. If I take the absolute value of a positive number, it doesn't change. I'm taking the absolute value of a number and dividing it by the number that this becomes 1. Since x is positive, this is 1/2 times 1, since x is positive. And so that would be 1/2. Now, if we follow the same sort of process on this next example, notice that we have the limit with x approaching negative infinity. All of the reasoning is the same. So let's see, let's take it to this point. We'd have 1/2 limit x approaching negative infinity of absolute x over x. Now let's think about what happens here. I have a negative number. I have a negative number that I'm substituting. The absolute value of the negative number becomes positive. It changes the sign. And so I've got a different sign in the numerator than I have in the denominator. Otherwise, they're the same number. And so then this becomes 1/2 times negative 1. Again, this is because since x is negative in this situation. All right, I have a limit at negative infinity. That means x is a negative number, and this limit is negative 1/2. And so this function has different limits whether we put in an infinity or a negative infinity. And we'll often see situations like that when we have roots involved in limits at infinity or negative infinity. There's a few special limits that we want to be aware of. So some special limits at infinity that we need to be aware of. So here, this is the function e to the x, or more generally, it's a to the x with a greater than 1. All right, and so here what I see from this is that the limit as x approaches negative infinity of e to the x is 0. Right? I have this e to the x, I'm moving far to the left, the limit approaches 0. However, the limit as x approaches positive infinity of e to the x is infinite. And the second function, do you know what it is? This is the function e to the negative x, or a to the x with a between 0 and 1. All right, so if we have this function, then I'll just talk about the e to the negative x, because that's what we tend to use the most. It's a horizontal flip of e to the x, and so we get, in a sense, a flip of those limits. the limit with x approaching negative infinity of e to the negative x is infinite, and the limit with x approaching positive infinity of e to the negative x is 0. And then finally, this curve is the curve arctangent x. So this is tangent inverse x, or it's sometimes written as arctan of x. And this has special limits. If you remember the graph of this function from back in your trigonometry class, the limit as x approaches negative infinity of this function, I'll just use the inverse notation, arctangent x. This limit is negative pi over 2. And the limit with x approaching infinity of arctangent x is positive pi over 2. So these are just some special limits you need to be aware of that involve infinities, because we tend to use them in certain places. So here's a few limits that we want to evaluate, and none of these are immediately we can't evaluate them immediately. We have to do some sort of trick on each of them. All right, so if we wanted to find the limit with x approaching infinity of e to the 4x minus e to the 6x, we might look at that and say, well, e to the 4x is going to behave like e to the x. The limit at infinity of e to the 4x, that's going to be an infinite value. And minus an infinite value, you might say, well, 0. You've got to be careful. Infinity minus infinity is an indeterminate form, because we don't know how those various different levels of infinity are behaving. We have to use a little bit more understanding. So what I'm going to do here is I'm going to do some tricky factoring. I'm going to write this as the limit with x approaching infinity, and what I'm going to do is I'm going to factor out the greater power. So here, between e to the 4x and e to the 6x, I would factor out the e to the 6x. So this is e to the 6x times, e to the 6x times e to the negative 2x. That would give me e to the 4x minus 1. All right, now let's think about this. If I try to substitute infinity, e to the negative 2x is going to behave like e to the negative x. And so that's going to give me a 0. E to the 6x is going to behave like e to the x, and that's going to be an infinity. So then this becomes an infinite value times 0 minus 1. That's an infinite value times negative 1. That's negative infinity. The limit with x approaching infinity of e to the power 3 minus x cubed over x minus x squared. All right, so if x is approaching infinity, then in the numerator we can simplify this. So this is a little tricky here. We got to use the technique we saw earlier in the section. So this would be the limit with x approaching infinity, and that's e to the, and what I'm going to do is I'm going to multiply numerator and denominator by 1 over x cubed in the exponent. So then that's e to the 3 over x cubed minus 1 over 1 over x squared minus 1 over x, or plus 1 over x. So now let's see what happens. In the numerator I've got a negative 1. In the denominator I've got a 0, but it's going to be a positive or is it going to be a negative? In this case, I'm I have a 0 plus 0, but both of these are going to be positive. Since x is a positive number here, this is going to be a small positive number. So what happens then is I then have e to the negative infinity, in a sense. All right, if I take that limit, I get e to the negative infinity, which is a 0. Similarly, in the second example, here I'm going to negative infinity. Nothing really changes in the numerator. The numerator would still be negative, but in the denominator, the x plus x squared becomes, what happens here is if I use the same idea here, I take the 3 over x cubed minus 1 over 1 over x squared plus 1 over x, but now I substitute a negative infinity. Now, 1 over x squared is a small positive number. It's a very small positive number, but 1 over x is a small negative number. Okay, and so what happens here is this becomes e to the positive infinity, which is infinite. Another way to approach this, kind of using an idea that I mentioned earlier, is if we take the lead terms here, the negative x cubed over x squared, that's going to behave like negative x. And if x was going to negative infinity, negative x, remember, if you think about how to graph negative x, as x goes to negative infinity, the output goes to positive infinity. And so that's where that comes from. So a couple different ways to think about it. All right, now the last one here. Let's see. I have the limit at infinity, the limit with x approaching infinity, of the tangent inverse of 5x to the 4th minus 6x to the 5th. So this is going to rely on a little bit of understanding that we saw back in an algebra course. And so if you remember something about polynomials, the end behavior of polynomials really only depends on the lead term, the term with the highest degree. So I really need to focus on this term, the negative 6x to the 5th. And so if you remember from algebra, if we had an odd power on the polynomial, the end behavior went generally from down on the left, up on the right. However, since it's a negative lead coefficient, that changes things up. It would be up on the left, down on the right. So then the limit as x approaches infinity, right, as I move far to the right, the limit as x approaches infinity is negative infinity. So this then becomes basically the arctangent at negative infinity, which is negative pi over 2. All right, so those last few situations are a little tricky, kind of tough to sometimes think about these limits at infinity. But if you think through it and understand what's happening with the expressions in the inside of the function, that'll help you understand what's happening to the function itself. All right, so that finishes up this topic with limits at infinity. I hope you found it slightly interesting. If not, well, hope the next one's better. All right, see you then.